Hey, Intro Engineering Design folks. This is a worksheet that I handed out, and I wanted to let you know about it. If there's anything you have questions about, I just kind of want to mention. This follows up after the end of that lecture that I posted above this one. But density is one of the physical properties of matter. This whole worksheet, I'm not going to read it to you, but usually, I'm not going to read the whole thing. Density is mass divided by volume. So how much mass you have per how much volume you've got. That right there, that comes up in one of the questions. One of the questions that has 3 parts down below. So you're going to divide whatever the mass is by whatever the volume they give you. Okay? So density measures how densely or tightly packed the particles are in a substance. And here's a table with some substances and some densities. Most likely these are at room temperature and at sea level-ish altitude. So they've misspelled Archimedes. That's my biggest complaint about this worksheet. Archimedes doesn't have an apostrophe there. It would be at the end if it's Archimedes possessive. Because Archimedes is his name. It has an S in it. Anyways, according to the Archimedes principle, if an object's density or a substance's density is lower than that of water, it's going to float on water. And that's true. There's a great experiment. Steve Spangler popularized a lot of these experiments, but I've done it before, where you take like a glass tube and you start pouring in super dense liquids at the bottom and less dense at the top. And even sometimes if you stir it up and let it sit for a few days, it'll sort itself out again back into the layers. And so you can see the different layers. It's really kind of fun, kind of gross, kind of sticky. But yeah, you can have this layers, the less dense on top, and they get more and more dense as it goes down. So that's true. If it's 1 gram per cubic centimeter, 1 gram per milliliter and cubic centimeter, the same thing. That's the density of water. If you have stuff that's about exactly almost 1 gram per cubic centimeter, it's going to kind of mix nicely with water. It's not going to sink or float. It's going to kind of be in the same strata. But if it's got a lower number like ice does, and you know that ice is going to float on water. You've had ice in a drink before. You've seen iceberg pictures, if you've not seen them in real life, but you've seen ice floating on the top of your drink, right? And that's because it's got a lower density than water. So what you're going to do is you're going to talk about, and number 1, it says, use Archimedes' principle, they misspell it again, to predict which materials in this chart up here are going to float on water. And let's list them. So you go through, you go ice, you look at anything here that's got less than 1, that goes in the float on water pile. Human fat floats in water. Yuck, how'd they figure that out, I wonder? Ew. So now we're going to use Archimedes' principle, it's not spelled right, to predict which will sink in water. So you go through anything more than 1 gram per cubic centimeter, that's going to sink in water. If it's just like a chunk of lead, it's going to sink. Iron will sink, things like that. So just list them out. Find which one's the most dense, which one's got the largest number in the density column, and which one's the least dense, find the smallest number. And then this is where you divide your mass by volume for each of these. You might need a calculator. If you don't, that's great. If you do, that's great. I don't care if you use calculators or not. I know some math teachers have a preference, but I don't mind either way. Then the second thing that we did, I don't have anything ready to show you. The second thing we did, I can describe it. You may have done this before in the past, is, and you can do this at home easily as well. If you have like a bunch of pennies, or if your dad or mom or someone has like some nuts and bolts that they've got, if you take just a little tiny square, 6 by 6 inch square is what I've been using in class, 6-inch square. If you take one of those and try to sort of form it into a boat, and you can see how many pennies or how many bolts it'll hold. I don't have pennies here, so I use some of the bolts that I have for my VEX kit. And I've got someone's boat held up 400 or so little bolts, and some other boats only hold up like 30 or something. And that's partly due to the shape that they made their boats in. I wonder if I still have, I might still have it open. Let me see. I don't, so let's do shape. And let's go in and I'll show you something about these boats. Before I show this, I'm going to say that this might give away something about making these boats out of tinfoil. So like, if you want to just try it on your own first, then stop the video now. Don't watch the rest of it. Usually this is the thing I do last after we've all had a chance to try and look at the boats that are more successful and the boats that are less successful. And so, yeah, pause it or stop it now if you want to go try it without my commentary following. And so the thing that I was going to comment on, let me hide these planes. I don't need them. and the origin. And the sketch can be hidden. There we go. So we've got I've made some little, basically boxes. And a lot of folks found that the most successful shapes were the ones that were like the flattest, the widest shapes. Like there's some people who made boats that were kind of little cupped and some that were kind of flat with a little bit of the sides folded up around the edges, almost like a box with the top missing. And the ones that made the boxy boats usually ended up floating more of the bolts, the steel bolts I have. And that's one thing that I heard a lot of people saying is, oh, it's because of surface area. You need more surface area. Well, surface area doesn't have much to do with density or with buoyancy, not directly anyways. But what happens is if I have less surface area, then the amount of volume, like if I push it down a full inch, there's not as much volume as if I did the same thing with another larger box, more surface area. And I kind of want to, let me save a copy of this because what I've done here is not exactly what I'm talking about right now. So if I were to go through and I try to think about different sizes I saw of boats, and I had people who folded up like just a half inch around the edge and people who folded up like more like an inch around the edge, and some people who just kind of folded the thing up in general kind of into a scoopy bowl shape, and they didn't have as much surface area at the bottom. If I go through my extrusions here and I make all of them extrude a full inch, let's just do that so we can see what that would look like. I didn't want to change it in the other one, only an inch. Not 2 inches. This one's 1 inch already. Okay. So which of these, like let's imagine these are all boats and there might be more to them. Like let me do this. Let me extrude the edge of the 4 edges too. If I add on to this an extrusion, oh come on. Okay, you know what? I'm going to click on these 4 and extrude them another inch, but I'm going to make a surface instead. Okay, now I get to click on, oh, come on. It's not working. I was going to extrude it up more so you can see like if the walls even kept going, but only this much of them is submerged. Like I can submerge more volume if I have a wider surface area. The footprint of the boat basically is wider. I can submerge more volume at that depth. And so I can put more mass in it at the same depth of submergence. So that's one thing to think about. Like it's not the fact that I have surface area. It's the fact that surface area then when it's pushed in the water, it's like extruding it and it becomes 3D volume that you're pushing under the water. And when you have like something that has bolts in it, it's got, yes, the heavy bolts in there and they do take up space, but it also has all that volume that doesn't have any bolts. It's all air. Air is much lighter than water. It's much less dense than water, I should say. Because like a lot of air will weigh as much as a little bit of water. Because air has mass, because otherwise it would float off into space and it would not stick to the ground with gravity. And air is made of matter. That's why it has mass. Where was I going with this? Look, I just got myself way off track. That has happened so many times today. All right. So yeah, if I've got a boat, this will be a boat, and it's just, this thing will probably sink in maybe this far into the water, not much farther. I put a lot of heavy stuff, like let me put my phone in it. That'll sink down a little bit farther, but all the space here that's below the level of the water, all that space below the level of the water that's not my phone is air. And all of that will make the overall density of the chunk of volume that's under the water lower. It'll make it less than water. It'll make it less than 1 gram per cubic centimeter. Even though my phone's kind of heavy because I got one of those big chunk and pretty big phones for the day and age I bought it in. And that's kind of the reason that the surface area is what matters. If I only have so much foil to work with though, like if I try to maximize that surface area and I don't have very high edges, then once those edges go below the level of the water, then you're going to start getting water come in and it's going to fail. But as long as I can maximize, there's a good ratio. There's probably math behind it. I'm not going to do the math. I'm going to stop talking about the math because a lot of people don't want to hear about the math. But it's not difficult math to do, especially if you make a square boat or a circular bottomed boat. One thing I also talk about is how a barge, let's do images. Barges in general, like they're used for carrying heavy things basically down river, upriver, or canals. They're very flat bottom boats. So they have that, as you think of it maybe as surface area, but they have a large amount of area that then gets pushed into the water, and that's a large amount of volume that it takes up of the space the water was in. And so that's how they can float so much stuff. Something like a canoe, the shape of the canoe, I mean, you can put people in a canoe, but you're not going to be able to pile on rocks in a canoe and ship that downriver. The canoe is more built with that point there and the wedgy shape that it has. It's more built for speed in the water than for carrying heavy stuff. And so that's, you think about things like aircraft carriers. They're pretty big. I want to see a picture of one outside the water. Notice how high up out of the water they sit, by the way. What is I wish I could make one of these turn around and see. Aircraft carrier, dry dock. Let's see what it looks like. So an aircraft carrier, you'll notice it has a wider surface for the landing planes on, but it also has a lot of this volume down below that's taking up. And it flares out at the bottom. Most of them do anyways. They flare out at the bottom, which means that they have more volume underneath. So anyways, I'm really fascinated right now by looking at boats. I'm going to stop because I'm going to get into a rabbit hole, and you guys don't need to sit around and wait and listen to it all. So take a look at this. This should be fairly quick and fairly easy. If you can't print it and write in the answers and take a picture and upload it, let me know, and I'll try to just rewrite these questions in Canvas as a quiz. But if you can print it off, then please do take a picture. Just let me know if you have a problem with it. And if you do make a boat, I want to know like the shape of it, like take a picture of the size of it. Tell me what you put in it and how much you got into it, like how many pennies or how many bolts, or if you put like a bunch of spoons in it. I don't know, whatever you find that you can try to float. I want to see how it goes. All right. Have a great afternoon or evening, whatever time of day you're watching this, and I'll see you again soon.